Hey guys, it's Mr. Kilburn, and I'm going to go through some examples of systems of equations solved by graphing, by elimination, by substitution. And I'm also just going to hit one last time what a function is, okay? Definition of a function, what it looks like, and then briefly nonlinear versus linear functions. So just kind of hit 2 or 3 different topics here. This will be the last ed puzzle you have till after the state test. So if it's a little longer, you just got to deal. So let's look at some examples, a couple of examples first of what it is to solve a system of equations by graphing. So look at the first one here on number 1. So you have 2 different equations, and you know that that's set up for graphing, not just because you see a graph, but because you see y equals, right? If it's in y equals mx plus b form, that way I know what the slope is, I know what the y-intercept is, and I can just graph away. Hang on one second. Where's clear? Oh, right there. Sorry. Okay, so let's get into this here. Let's graph the first one right here. Y equals negative 5,6x plus 2. Okay, where do you start to put your first dot? Okay, that's right, at positive 2 on the y-axis. The slope is negative, so do you start by going up or down? That's right, you go down. So you go down 5, 1, 2, 3, 4, 5, and then 6 to the right. 1, 2, 3, 4, 5, 6. So right there. Now I've only got space to draw one dot that way. So instead of going down 5, 6 to the right, I could go up 5, 6 to the left, like so. Okay, I could do that. Either way, I draw a line like so, and here we go. Okay, now on the state test, you're not going to actually have to graph because there's no short response. However, it could be a multiple choice like we saw today, where they give you a system of equations that's graphed, and then you take the graph and figure out, well, what 2 equations make up those 2 lines. So this is still applicable. Okay, next, to graph this line, you start where? That's right, positive 8. And the slope is positive 1/6. So you're going to go up how many to the right? That's right, up 1/6 to the right. And once again, I run out of space pretty quickly. So the opposite of going up 1/6 to the right is down 1/6 to the left, and it becomes very obvious where they intersect, right there at negative 6, 7. Remember, when you're graphing a system and they intersect, it's not just the x value, it's not just the y value, it's that ordered pair. In this case, negative 6, 7. Okay, let's try. I guess that's it for that one. Okay, so once again, graph the 2 lines, see where they cross, and if it's already done for you, the graph's already done up for you, you might need to figure out what those 2 equations are. Okay. All right, let's scroll a little bit here. Okay, look at this one, number 3. I'm going to change it a little bit just to make a point. Okay, suppose it was, instead of y equals 1/2 x minus 4, suppose it was y equals 3x minus 4. Okay, it looks like that. So for the first one, right, you're going to start at negative 9, and you're going to go up 3, 1 to the right, up 3, 1 to the right, and so on. And it's going to look something like this. And you go to graph the other one, you're going to start at negative 4, and you're going to go up 3, 1 to the right. And it's going to look like that. Okay, well, what's the solution to that system? Or where are those lines intersecting? Right, they're not. There's no solution. And why is there no solution? Because what is the same about those equations? That's right, the slope's the same. So if the slope's the same, they're not going to cross. So there's no solution. Okay, and if you see something like this over here, y equals 6/4x plus 1. Okay, well, if I graph that first line, I start at positive 1, and the slope's positive 3/2. So up 3, 1, 2, 3, 1, 2, 1, 2, 3, 1, 2. It's going to look like this. Now it's got a little sideways, but you understand. Okay, now I'm going to change colors here, but suppose I go to graph this one. All right, so instead of going up 3, 2 to the right, it tells me to go up 6, 4 to the right, but I still start at positive 1. 1, 2, 3, 4, 5, 6, 1, 2, 3, 4. And when I go to graph those, what do you notice? Oh yeah, it's the same line. Okay, so in that case, there's an infinite number of solutions. Okay, or infinite sign hashtag of solutions. Okay, so good little review of those. Next. It says solve each system by the method of your choice. So the two choices we worked on are solving by elimination and solving by substitution. Okay, so let's do number 5. We'll do it by elimination. Okay, so if you look, actually we'll start at number 8 first. Sorry, number 8. Okay, the way this is set up, okay, one of the two variables cancels out without doing any work. Which one cancels out without doing any work, the x or the y? That's right, the y, because a negative 4y cancels out a positive 4y. So then combine your x's, you get 8x equals 16, divide 8, and without a whole lot of work, you get x to be 2. All right, but we're not done, because I've got x, I don't have y, and when you're solving a system, you're trying to find the ordered pair where these two lines, these two functions intersect. Okay, so once I get y, I'm sorry, in this case, x. Once I get x, plug it in to get y. Which equation? Doesn't matter. So plug it into the first one. So instead of minus x, I'm going to have minus 2. Minus 4y equals 2. Add 2, add 2. I get negative 4y equals 4. Divide negative 4, divide negative 4. Y equals negative 1. So again, the answer is not just 2, it's not just negative 1, it's the ordered pair 2, negative 1. Okay, next, now scoot back over here to 5. So it reads 2x minus 6y equals 28, minus x minus y equals 14. All right. So I guess my question is, it's up to you at this point what you want to cancel out, either the x's or the y's. Okay. What would you multiply the bottom equation by to get rid of the x's? Okay, hopefully you said 2, okay, because when I do that, I get negative 2x minus 2y equals 28. All right, well, positive 2x, negative 2x, they cancel. Then I can combine my y's, and I get 4y equals 56. All right, divide 4, y equals 14. And once I get y, I plug that back in to get x, just like over here. Okay, but to save time, I won't do that. Okay, what if you wanted to get rid of the y's? What would you multiply the bottom equation by to get rid of the y's? Okay, yeah, hopefully you said a negative 6, because watch what happens. When I distribute this negative 6, I'm going to get 6x, because negative 6 times negative 6 times negative 1 is a positive 6. Negative 6 times negative 1 is again positive 6. Don't forget the y equals 8. No, 14 times 6, 4, 5, 6, 64. And negative times positive is negative. Okay, so once I do that, the y's cancel, and then combine my x's, and you get 8x equals 34. No. 34, 54, 44, 34, 36. Yeah? Hang on. 64. Oh, wait, this should be 84, not 64. Sorry. So 84, 74, 54, 56. There we go. Now I got it. X equals 7. Once again, I'm not going to go through and figure out why, but if you needed to, once you have x, plug back into one of those two equations, and you'll get y. Okay, so that's elimination. Let me find a substitution here. Let's set up for substitution. 19. Okay, so when you're if you need to solve by substitution, you're going to see either x equals or y equals. And then another equation that is in that kind of form. Okay, So y equals 4x plus 18. So where I see a y, I'm going to replace it with 4x plus 18. So I've got negative 4x minus, and then again, I'm going to replace that y with 4x plus 18. And the reason I do that is because now I have an equation with just x's in it, just one type of variable. And I'm going to, at this point, distribute my negative 1. So I'd have negative 4x minus 18 equals 32, 14. Good grief. Okay. Now combine like terms. I get negative 8x minus 18 equals 14. Add 18 to both sides. Divide negative 8 to both sides. Like so, negative 4. Once again, once you get x, plug it back in to get y. So in this case, I'd probably use this first equation because it's already y equals. So once I plug in my x here and evaluate it, it becomes pretty easy. 4 times negative 4 is negative 16. So I get y equals negative 16 plus 18, which is 2, giving me the ordered pair, negative 4, 2. That's the answer. Okay, so there's elimination, there's substitution, we did graphing. Okay, now briefly, let me scooch over here, change my share screen. Stop share. I'm going to share this here. Okay, whiteboard. So real quick, a function. A function is a rule where each input goes to one output. Okay, so suppose I have this. This is my inputs, and over here, my outputs. You can think of these as your x's and these as your y's. So if I had, suppose I had 3, 2, 9. And over here I had 6, 1, 8. And 3 goes to 6, 2 goes to 1, 9 goes to 8. That's a function, okay? Each input has one buddy, goes to one output. But as soon as you have something like this, where 3 goes to 6 and 3 goes to 1, now it's not a function. Because the x values, in this case 3, there's an x value with more than one, assigned to more than one output, more than one buddy. That's not a function. What it looks like as in a table is something like this, where you would see 4, 2, 3, 4, 8, 7, 1, 9, 5, whatever, 13, okay? 4 goes to 7, 2 goes to 1, 3 goes to 9, 4 goes to 5. Well, you've got 4 going to 2 different outputs, so that's not a function, okay? As sometimes it's a set of ordered pairs. So you'd have 3, 1, 6, 8, and 3, I don't know, 9, whatever. Okay, 3 goes to 1, 3 goes to 9, not a function. Okay, each input can only go to one output. Lastly, nonlinear function. So we touched on this briefly. And a nonlinear function is a function in which the variable has an exponent other than 1. Okay, so this would actually graph something like this, and you'll see these next year. They're called parabolas. This is called a quadratic function when the leading coefficient, when the largest exponent is 2. As a graph, I mean, any kind of a curve, right? I mean, I don't know. If it looks something like this, that's nonlinear. Okay, a linear function is just what we've graphed for most of this year, just a straight line. Okay, so that's the difference between nonlinear and linear. Nonlinear has different slopes from here to here, from here to here. The slope's always changing. With a line, the slope never changes because it's constant. But the big visual, the quick visual, is when there's an exponent other than 1. Now, before I forget, lastly, there was a state test question a couple years ago. I'm not sure if it's going to be on tomorrow's or not, but it asked something like this. Is this linear or nonlinear? That's what it was. Y equals 1 over x. Is that linear or nonlinear? Well, at first glance, you might say, well, wait a minute, there's an exponent of 1 right there, so it's linear. Well, but remember, if that x is in the denominator spot, we talked about this with our laws of exponents. This could also be written as y equals x to the negative 1. And clearly negative 1 is not 1. Okay, only equations or functions in which the variable is raised to a power of 1, those are linear. But clearly that's not getting raised to 1, it's getting raised to negative 1. So it was kind of a tricky question. Students struggle with that. It might have been 3-4 years ago, so I doubt they'll use it this week. But if you see something like that, this is definitely nonlinear. If you were to graph it, you would see it, but the visual is the exponent is something other than 1, in this case, negative 1. Okay, I know I touched on a lot of stuff there, but one last ed puzzle for you to do is prepare for either Thursday or Friday, depending on when you get this. These other ed puzzles you should have done or should be doing, take advantage of those. No more paper homework till next week. That's all I got. Okay, hopefully you got the seafood mornay today at lunch. I mean, yummy, super yum, wicked yummy. All right, guys, have a great day. Take care. Later. I am out. Peace. Let me try that again. Peace.